Okay, this is sample problem vector space M11, and basically it comes down to this. V is in the set of two-dimensional column vectors from the complex numbers with the usual vector addition. In other words, if we add the elements of V, X, and Y, then we just follow the ordinary method of vector addition. We add elements horizontally in the right positions. But the key is the multiplication, scalar multiplication is redefined. So for this particular vector set, whenever I multiply by a coefficient alpha, which is also a member of the complex number set, it not only multiplies as a coefficient, but it transposes the elements of the vector. So y becomes x and x becomes y after multiplication, and we do the multiplication, right? So that's the rule. Basically, when we do scalar multiplication, we always displace x and y. We replace them with each other. So the question is, does this then form a vector space? And to form a vector space, you have to have two things defined. You have to have addition in the space defined and scalar multiplication. And because those are both defined, it checks the first box, which is, it's a vector space if it has those two things defined. The problem is there are 8 other properties for a total of 10 that also have to be defined, and they basically have to follow the rules. We can redefine vector addition and multiplication, but we can't redefine the properties that come from that. And one of the first ones we'll look at is the associative property of scalar multiples. Because alpha is a scalar, let's take a look at SMA. This is one of the 8 properties that has to be fulfilled. It basically means the scalar multiplication associativity. And here's what has to be true in order for SMA to hold true. If I take 2 coefficients, alpha and then beta, and I multiply that by u, and u in this case is going to be, let me write it over here, u is going to be an element of this vector space that we've just defined, okay? So if I do them in this order, where b is multiplied by u first, and then I follow it with alpha by following the order of operations, that says it's supposed to be the same thing as if I take the 2 scalar coefficients and multiply them together, and then I multiply them by u afterwards. So it's basically about order. The order of operations can be b first, and then alpha second, or it can be alpha first and then b second, but ultimately it doesn't matter what the order is. It has to be the combination of alpha and beta, the 2 constants multiplied by each other times u. And of course, this particular one under this set of rules fails. Let's go ahead and show it. So if I did alpha times beta times u, and in this case, let's give u a specific definition. Let's just call u x over y. So it kind of represents the general element of v, okay? So that would be alpha times, once beta is multiplied inside, it's going to be beta times y over beta times x, because I've employed their rule for multiplication. And now we multiply alpha, so it flips it back. So that's going to be alpha beta times x over alpha beta times y. Because I did 2 instances of scalar multiplication, I basically had to apply this rule twice, once for beta and then once for alpha. But if we multiply alpha by beta, that's going to make a single new constant. I can just call it alpha beta. I could basically assign it another variable if I wanted, but because these are members of the complex number set, they're just going to form a new constant. And of course, if I do it that way, alpha beta u, if that's equal to alpha beta times u, then that's going to produce one single instance of this flipping. So it's going to be alpha beta times y over alpha beta times x. And you can see there is a difference between the final answer, and so this is not held to be true. And that means if I define a vector under these first 2 rules, that vector will not form a vector space because it fails one of the 8 following rules, which must remain consistent. We can define these any way we want, but we have to define them in ways that don't violate things like the associative property. So this is a big no. This is not a vector space.